No. Don't read. Why your hands so? Okay, we are going to meet my favorite chemist today, Tyler DeWitt. He's like a teaching genius. He's been making these videos for years and years now. Right? And we are going to start with atomic models. And this is on page 5. Okay, page 5. Page 5. Okay. Oh, I think we're still muted. Hang on a second here. Unmute. Okay, here we go. I have dropped myself a copy, so I'm going to need to put things in. How many of you studied the atom last year in grade 8? How many of you learned anything about the atom last year in grade 8? About half of you, maybe 2/3. Okay. All right. Doesn't matter. We'll learn it from scratch just in case you didn't. Here we go. Okay, so that is our first box on there. There's a little box around 2,500 years ago, and you're going to fill that in. Not that you need to memorize that number or anything, but just be impressed by how long ago that was. That was a long, long time ago, and these two guys actually had some really, really powerful ideas about the atom. And then people let those ideas go. It was crazy. They were like, no, you guys are wrong. Too bad. So sad. Sorry. I'm just going to put on the subtitles. So you're going to fill in the box beside atomos with the word uncuttable. And he really did have the right idea. If you cut something in half and in half and in half and in half, you will eventually get to the smallest piece of matter that still has the properties of that element. Not that you can't split atoms, but it's really difficult. And we have to do some fancy nuclear chemistry. But these poor guys, then they were forgotten. People were like, almost 2,000 years will go by before we think about these ideas again. Crazy. Okay, so whose model is this? Dalton, D-A-L-T-O-N. Dalton's model of the atom. Now, I want you to take a look at the very bottom right-hand corner. This model is called the what model? So at the bottom of the page, down there, it's called the billiard ball. Do you guys know what a billiard ball is? It's like pool. So if you play pool, you know, with the cue, you know, you're right. A billiard ball is the ball that you play with. Okay, those are pool balls. But if you think of if I call it a pool ball, then you might think it's like a beach ball. Not that kind of ball. Okay, not a beach ball. Now, think about a pool ball or a billiard ball. What are they like? Describe a billiard ball to your neighbor. What are they like? What are some words that you use to describe billiard balls? Who's got a word or two to describe a billiard ball? It's a spherical object. It's got numbers on it. We're going to ignore the numbers for now. Although each atom, each element actually has its own individual number, which we will learn about later. So it's almost very fitting that the billiard ball model has the billiard balls have numbers on it. Are those billiard balls, are they hard or soft? Hard. They're hard. Can you split them in half, or are they just indestructible essentially, unless you like take a jackhammer to it or something? You could split them in half, but you'd have to take a sledgehammer to it. So let's just say you can't split them in half. So let's take a look at a little bit more about Dalton's model. Yes?
Wait, what does that thing say at the end?
At the end?
Like, you know,
Oh, matter consists of indivisible atoms. That's the first one. Indivisible. Not invisible, indivisible. Okay, and in fact, let me write those words down for you in a pen that works. So matter consists of indivisible, which essentially means uncuttable. Yes? It does not mean invisible. Okay, they're not invisible. Although to the naked eye, they are invisible. You cannot see a single atom. They are too small. And then we have atoms arranged in different combinations. To make different compounds. Okay, so down in this little area here that Tyler is hiding with his hand, Those three blanks are indivisible, I can say it, combinations and compounds. All right. Okay, and you can see that is an atom. This thing here is a combination of atoms. That's what we call a compound. We have a yellow atom with 4 red atoms. Here we have a compound that's made of yellow, orange, and pink. Okay. Okay, we're going to pause here so we can fill in our blanks. This is called the plum pudding. Plum pudding model of the atom. Plum pudding. Has anyone here ever had plum pudding? There are no plums. No plums at all. And in fact, we're going to take like a little side tour off to find flaming plum pudding. Okay. This is the one we want. Okay, I used to love doing this because it would take place right at Christmas. Plum pudding is a traditional British Christmas dessert. And we're going to show you what they normally do with it, okay? Normally they flame the plum pudding. So he's going to show you how you might actually do this. This is not like required science, but it is interesting. And one thing I want you to notice, if you can see them, there are sort of like little bits and bobs in here. Yes? Raisins. Plum pudding does not contain plums, it contains raisins, because it turns out in Victorian England, the word plum just meant dried fruit. Okay? So that's why plum pudding does not contain any plums, it's just dried fruit. But it gets more exciting because he's going to flame this lovely pudding. Okay, so that is a plum pudding. So if you're like, what the heck is this plum pudding model? What are they talking about? They're talking about this traditional English dish. Sometimes it's in the shape of a circle. Like they'll make the pudding and they'll wrap it in a piece of cloth. They actually make it over the course of a year, usually, and they keep pouring brandy over it. And then the alcohol evaporates, but it leaves the flavor. And if you're a child, unfortunate enough to try some of this, it actually usually tastes pretty disgusting because it's got all this flavor of the brandy, although the alcohol, like I said, the alcohol has all evaporated, but it's got this brandy flavor, which as an adult, I'm like, it's delicious. But as a child, I remember trying it for the first time and I was like, what is the nasty? Anyway, so fortunately, they also had brownies, which was a good backup plan for anyone who did not like that flavor. All right. Back to Tyler. Now, take a look at this plum pudding model. What do you notice about this model that might make it look kind of like a plum pudding? Yes. Yeah, the electrons are like the raisins, and this sort of round thing is like the pudding part. Yes? Very nice. All right, so let's fill this in while we're here. This is our plum pudding model. It is by J.J. Thomson. That little negative thing is an electron. Okay, and then on the box on the right, positive, we fill in positively charged pudding. Okay, so that is our positively charged pudding. And by the way, if you should miss any of these things when you're filling it in, the answer key actually has it filled in as well, so you can always go back and check in there if you have to. Okay? Okay. Okay, so big ideas of Thomson's model. Big ideas of Thomson's model. We have electrons, which means that the atom is not indivisible. There is smaller stuff. And probably tomorrow, not tomorrow because we have our test on whatever the next day is, Friday, we're going to look at the experiment that said, hey, there are things inside there. All right. But we also have both positive and negative because atoms are electrically neutral. Do you guys know what neutral means? Things can have an electric charge. They can either be positive or they can be negative. But if you have a positive and a negative, they cancel each other out and it becomes zero charge, which is neutral. And all atoms are neutral. So if there are these little negative things, there must be also positive stuff so that overall it is neutral. Okay? Okay, so here we have the nuclear model, Nuclear, and that is by Ernest Rutherford. All right, and what do we call that little positive thing in the center? That is the nucleus, that is the center. Have you heard the word nucleus before?
Yes.
Yes? Where have you heard that before?
So.
In the cell. Where is the nucleus of the cell? In the middle. And where is the nucleus of the atom? In the middle. Okay, so this is one of the blanks that you're going to fill in. It says all the positive charge of an atom was concentrated at its, well, you could say at its nucleus or at its center. Okay? And besides that, you do have some electrons floating around out here, but what's in between the electrons? Nothing. It's just empty space. So if we are looking here, all the positive charge of an atom was concentrated at its center, which is the nucleus. Besides that, atoms were pretty much empty space. Okay? Okay, so this is the Bohr model, which is spelled in a sort of strange way, B-O-H-R. B-O-H-R. Okay, so this is the Bohr model by Niels Bohr. This one's really easy to remember as long as you know one of the names, the scientist or the name, you know the other one. Okay, and in this one, he called this little circle an orbit. Just like planets orbit around the sun, he thought that electrons orbit around the nucleus. Okay, so we're just going to pause for a second and make sure we got that blank filled in. Oh, it's thinking. Electrons go around the nucleus in orbits. At specific distances from the nucleus. So you know how the Earth is the third planet from the sun? And it always goes around in its orbit, and it's not like jumping out to where Mars is or anything like that. That's what he thought electrons were like, that they all had a specific distance that they liked to be at. And we're gonna pause for this one because, man, we got some writing to do here. We have the quantum mechanical model. All right, I'm gonna fill this in along with you because it's kind of crazy. We have the quantum mechanical model. Quantum mechanical model. I don't even know if you can fit that all in there. You have to write pretty small. And the guy's name was Irwin. And then it's not just SH, it's SCH. Schroe. And then Dinger. And the Dinger part is pretty easy to spell. Okay, so we have SCHRO, Schrödinger. Yeah. And he didn't call his things orbits because nothing was really orbiting. He called them orbitals. And this year we will take a little look at what those are actually like, but they are pretty mind-bendingly weird. Okay? Small stuff is very, very strange. So we'll get the flavor of them this year, but we won't look at them too much. Okay? Here is another orbital. And just while we're here, electrons don't spin in orbits. They are more like hyperactive flies. And they buzz around the atoms, sketching out different shapes. If you take time-lapse photography of a hyperactive fly, you would see over time that it sketches out a particular shape or a particular design. So you can imagine that little electron zipping around the nucleus. Yes? And it would form like a spherical pattern. It looks like a circle here, but it's three-dimensional, so it would be a sphere. Okay. Okay, so the hyperactive sketchout shapes are called orbitals. All right, here we go. The hyperactive sketchout shapes were called orbitals. Why am I pen not coming up? There we go. Some of these shapes were spheres, and others look like two, I don't know what he's going to write there. So we're going to go back. I think they look like two balloons. Two balloons? But we're going to find out what Tyler has to say, because I don't know what he has to say. Teardrops. But you can say balloons. Okay, so we can fill in teardrops. Okay. Yeah. Okay, so we have, once again, the quantum mechanical model. This is at the bottom of page 7. Quantum mechanical model. And it has protons and neutrons. How many people have heard the words protons and neutrons? Yay! Okay, and if you haven't, don't worry. You will hear them a lot during the next few weeks and they'll become very familiar to you. And if we look at the picture, I'm just going to get rid of the subtitles for a moment. Where do we find the protons and neutrons in this model? In the middle. So that means where are they located? They are located in the nucleus. The nucleus is the center. And because the protons and neutrons are in the center, they are in the nucleus. And in fact, we could even add that onto our little diagram here. Okay. So we have our quantum mechanical model. With protons and neutrons. Once again, we have protons discovered by Ernest Rutherford. And neutrons were discovered by James Chadwick. We have the protons and the neutrons. And they are in the center. They are located in the nucleus of the atom. And this here is an orbital. And it contains, what does an orbital contain? Electrons. Protons and neutrons in the center, electrons around the outside. And that's pretty much our current understanding of the atom. Thank you. So this, you can see the development of models as they did different experiments and found out new things. All those models changed over time because that's how science works. They come up with one thing and they're like, oh, this is a good idea. This must be something. And then they were like, okay, well, we don't just have a nucleus, we have orbits around the nucleus. And then they're like, oh, well, that doesn't really work because we got some new evidence that showed us that they don't actually go around the nucleus. They actually go around like little hyperactive flies. And maybe last year you might have learned about some strange things called leptons and quarks. Anyone learned about quarks last year? Okay, those are even smaller, and we will not be dealing with them this year because they are too esoteric. They're kind of like highfalutin kind of things that we don't use very much. Okay, so what we're going to do is we are now going to go and answer a question that is on here, on page 8, I think. Ooh, just before we go to page 8, we need to wake this thing up again. I want you to notice right at the top of page 7, the quantum mechanical model has another name. It is also known as the electron cloud model. Why do you think they call it an electron cloud model? Tell your partner, why might they call it an electron cloud? Could it be because this kind of looks a bit like a cloud? Yes, that's exactly why. Okay? Now, on to page 8. Bohr model, less accurate. But useful. And I'm going to show you an example of why. You guys are familiar with water? Do you know the formula of water? H2O. There's a very good reason that it's H2O and not H3O or HO2 or anything like that. Here is a Bohr model of a hydrogen atom. It has 1 proton in its nucleus, and it has 1 electron on the first, we actually call them shells, okay, or energy level. Now, it turns out hydrogen does not want to have 1 electron on its shell. It wants to have 2. Turns out that's very stable. We'll talk more about this later. Oxygen, and I'm going to draw it in red so you can see the difference. Oxygen has 8 protons. We're going to ignore the neutrons just for now. It's got 2 electrons on its first shell. And then it has 1, 2, 3, 4, 5, 6 electrons on its second shell. And if you're not able to draw this, don't worry, okay? Well, it's not critical for you to be good at this point. It has 1, 2, 3, 4, 5, 6 electrons on its second shell. But it turns out it does not want 6 electrons, it wants 8. So we have hydrogen that wants to have 2 electrons, and we have oxygen that wants to have 8 electrons on that outer shell. So what's going to happen is hydrogen is going to come over here, and it's going to overlap with oxygen, and they're going to share those 2 electrons. And we're going to get another hydrogen down here with an electron. And this one up here is an O atom. And these 2 guys are also going to share electrons. So now I have my oxygen atom, which has 8 protons in the nucleus. It's got 2 electrons on its first shell. And then in its second shell, it had 2, 4, 5, 6. And like I said, if you're not able to draw this, don't worry about it. But now hydrogen overlaps. And do you see how now hydrogen now has 2 electrons just like it wanted? It wanted to have 2, and now it's got 1 from itself and 1 from oxygen. So now it has 2. So hydrogen is satisfied. Okay? Now we have our second hydrogen atom down here. And it has an electron. And you see how now this hydrogen down here also has 2 electrons? And remember how oxygen wanted 8? Well, now it has its own red 1, 2, 3, 4, 5, 6, but each hydrogen is also sharing an electron with oxygen, giving it 8. And that's why H2O makes H2O, because it takes 2 hydrogens to fill up that outer shell of oxygen, and oxygen will fill up those outer shell of hydrogen. Now, the whole moral of this story, like I said, you don't need to know how to do this. Could you imagine being able to draw this with these crazy diagrams? No. And then there would be maybe like that other one that was squiggly like this, right? And you'd be like, now I got a bat. And now I got one up here and one down here. And it's just too crazy. You cannot show things very simply. But the Bohr model, why would we use the less accurate Bohr model? Because it makes showing bonding really simple. It makes picturing electrons really simple. This is not simple, right? That's crazy, man. It makes it simple. Now, do you remember Dalton's model? Dalton was number 1. What did we call his model? What did his model look like? Billiard ball. Can you think of a time when it might be nice, instead of even using a Bohr model, to go even simpler and make it a billiard ball model? What if you wanted to draw a bunch of water molecules? And every time you had to draw a water molecule, you needed to draw that. What if you had to draw that every single time? Would that drive you crazy? Wouldn't it be nice just to be able to say H2O and maybe another H2O and another H2O? So there are different scenarios where it's useful to use the simpler models, even though we know they're not super correct, right? And that takes us to the end of this, which takes us to 5 minutes before the bell. And you have a test tomorrow. So I think we should just leave it right there. I think that's perfect. Okay. So you guys can just relax for 5 minutes. Remember, you still cannot go on your phone. Right? No phones. Because we're still in this classroom.
Bro, no one feels bad. My game. Yeah. Exactly. Yes, you don't have a lesson. Oh, it's I told you. Of course not. Yeah, I know.